Hello, my name is Stavros Maroulis, and I will present you our work titled RawVis, a system for efficient in situ visual analytics. This is a joint work with Nikos Bikakis, George Papastefanatos, Panos Vasiliadis, and Yannis Vasiliou, and is presented in the demo track of the 2021 Sigmund conference. Our work is in the context of in situ data analysis, enabling users to visualize, explore, and analyze raw data without the use of a DBMS. In in situ data analysis, data scientists wish to visually interact and analyze large raw data files, for example, a CSV file. These users usually have limited skills in data management and limited resources or commodity hardware for use. Data are in raw format in files that do not fit in main memory. In such scenarios, users need to interact and perform the analysis with visual ways, directly over the raw files, avoiding the tedious tasks of loading and indexing the data in a data management system. They expect fast response times and usually start their analysis on specific parts of the dataset and perform exploratory analysis around these areas. We have implemented RawVis, an online tool which addresses the need for interactive visual operations and analytics directly over big raw data. It offers users the ability to visually interact with the data on the 2D space, such as exploration of data points on maps or scatter plots, along with visualization of data attributes, mainly attributes with categorical values in various charts. Finally, various statistics and analytics operations can be computed on visualized data points and presented to the user. Our tool is powered by a lightweight index, which is constructed on the fly, supports visualization-aware query evaluation based on user exploration, and adapts the underlying index as the user explores more parts of the dataset. The underlying technology and research work behind RawVis includes the following. First, we start from an exploratory user-oriented approach, and we formulate visual operations over spatial and categorical attributes as data access operators. We then propose VETI, a hybrid index that combines tile and tree structures and supports in situ exploration and analytics over categorical, numeric, and spatial attributes. We address the need for fast data to analysis, and we propose efficient index initialization from the raw files given memory constraints a user may have. Finally, we optimize query evaluation over the index in order to minimize I/O and response time. For example, we access the raw file in a sequential manner, and we use, where possible, cached metadata for memory-based computations. Most importantly, we progressively enrich the index as users navigate to unexplored areas. The VETI index is built in memory and combines a grid for the exploration in the 2D plane with a tree structure for operations on categorical attributes such as filter and group by. VETI is primarily organized in tiles based on two attributes that define the exploration on the plane. For example, on a map, usually these are the longitude and latitude, but any other numeric attributes can be used as the two-axis attributes. Each tile may have subtiles breaking the space into more fine-grained areas. For each tile, we keep its interval, the ranges of the two-axis attributes, and its children. Each tile is then connected with a tree that we call categorical exploration tree. This categorical-based tree is a lightweight tree-like structure which organizes values of the categorical attributes into levels. Each tree level corresponds to a different categorical attribute found in the raw data, and each node corresponds to a value from the domain of an attribute. For example, here, Samsung, Apple, Xiaomi, and Huawei are placed in the last level of the tree in the picture, which keeps values for the brand of the devices in the raw file. In this way, based on the tree hierarchy, each node is associated with a set of objects based on the node path. References to the records in the raw file are stored in the leaf nodes of its tree. They point to the offset of each record in the file. Finally, leaf nodes keep metadata such as counts, sums, or averages of numeric attributes that are commonly requested in the charts and help us avoid access to the raw file. In our working scenario, we consider that users visually explore the data stored in a single CSV data file on disk. They primarily analyze data on a two-dimensional plane, for example, a map or a scatter plot, and further on, use visual ways for the analysis of the data, such as bar or line charts, heat maps, and various statistical methods, for example, a Pearson correlation on two attributes. At a glance, our tool translates its user visual operation at the front end into a query in the back end. At the left side, the front-end interface is depicted, and at the right, the back-end architecture. In the back end, the first time the user requests to visualize or analyze a new dataset, the file is parsed and the index initialization component produces an initial version of the index. In parallel with index construction, the results corresponding to the first user request are evaluated. Based on the user exploration model, the user's visual and analytic operations are then translated to data access operations in the operation translation component. These operations are then evaluated over the index to compute and fetch the results. Based on the last user request, the index is adapted progressively, reorganizing its contents and updating any metadata. The query results are further processed and reduced to avoid overplotting issues. For example, clustering and aggregation techniques may be used before rendering the results in the visualization component. A key feature of our tool is that it builds the index the first time the users start their exploration. Initially, a crude index is constructed without too many details to allow for fast response time. For example, we have no hierarchy of tiles nor many levels in the trees. Also, we built the index structure considering the amount of available memory resources. This initial index is, however, not balanced. We make it more fine-grained near the initial query to improve query evaluation during the initial stages of the exploration. Note that during the index construction or the query evaluation, the index structure may not fit in main memory. In such cases, the eviction handler component stores parts of the index structure to the disk. For the query evaluation, we adapt the structure of the index on the areas the users visit, and we employ query evaluation techniques in order to reduce the I/O to the raw file. As presented previously, its visual operation is translated to a query. This query is executed over the index, which decides whether access to the file is needed or not. First, when access to the file is needed, it is made in a sequential manner to avoid random or multiple access to the file. Next, we rely on computed metadata stored in the index to fetch previously computed results. This way, we avoid going to the file for a variety of statistics that can be computed online by the metadata of the index. Finally, after its query, we adjust the index structure and the contents in order to compute and store metadata that may be of use in the next interactions of the user. We do that by splitting large tiles into smaller ones and reorganizing the objects such that metadata can refer to smaller areas. This allows subsequent queries to fully contain tiles, avoiding the comparison of the query intervals with every single object. Also, we reorganize the levels of the trees in order to include attributes that the user requests but were not previously included in the index. All these adaptations to the index are made in the areas the user explores, and so the overall memory footprint of the index can be kept small. We have experimentally evaluated RawVis, comparing it with traditional approaches, such as loading data into an SQL database, but also with other tools that consider in situ settings. Here in the plots presented, the series that correspond to RawVis are the black ones where the arrows point to. We have shown that response time is in most cases in the order of milliseconds, even for very large files on commodity hardware. Also, our tool outperforms competitors in terms of query execution time, both in real and synthetic datasets. Most importantly, it achieves fast initial query response time, which improves over time as the user explores and adjusts the index. For the end user, the tool offers four basic functionalities. First, it offers map-based visual exploration for users to explore, analyze, and compare data over different geographical areas using operations like pan and zoom. Second, it offers faceted exploration so that users can define multiple filters over the categorical attributes. Third, it offers statistics computations so that users can analyze the data using univariate and bivariate statistics. Finally, it offers visual analysis so that users can analyze the data by selecting the most suitable visualization types and metric. A glimpse in the UI is shown in this slide, highlighting its primary main panels. At the center, there is the map visualization panel where data points are rendered and clustered. The user can draw an area and select specific objects contained in it. At the left side, there is the dataset information panel, where the users can select the source file, and the filtering panel, where users can put faceted filters on the data. Finally, on the right, there are the statistics and analysis panels, where statistics in various charts are shown. These are interactive and synced with the spatial operations the users can perform on the map and the filters that they apply. We will continue with a short demo which shows how users can interact with our tool. The use case we will examine in this video is the NYC yellow taxi trip dataset, which is a CSV file containing information regarding yellow taxi rides in New York City. Its object refers to a specific taxi ride described by several attributes, such as the pickup location, trip distance, payment type, passenger count, and tip amount. First, we can see in the dataset information panel that the selected CSV file is the taxi dataset. Below, the dataset attributes that correspond to the latitude and longitude for the map-based exploration are shown. Here, these attributes are the pickup latitude and longitude. Clicking on this button, the users can trigger the index reinitialization, which results in the raw file being parsed from scratch and the initial crude index being generated. At the bottom of the screen, users can examine performance info regarding the query evaluation. Every user operation results in a new query, with the query evaluation info panel being updated correspondingly. On the bottom left part of the screen, users can filter the data using the filtering panel. Initially, no filters are set. On the right, the statistics and visual analysis panels are shown. The statistics panel shows univariate and bivariate statistics for the objects currently shown in the window. In the visual analysis panel below, users can perform visual analysis of the data using charts, like this bar chart that presents the average tip amount of the taxi rides in relation to the number of passengers. On the map visualization panel, users can perform operations like zooming in, zooming out, and panning in order to change the visualized area and find areas of interest. Changing the visualized area updates not only the objects and clusters shown, but also their corresponding statistics and charts. To filter the objects based on the categorical attributes of the dataset, users can use the drop-down filters on the filtering panel. For example, to analyze only taxi rides that were paid for using a credit card, the corresponding filter needs to be selected. Also, multiple filters can be added. Again, filtering the objects also updates the statistics and charts shown. Users can select the numeric attributes for which they wish to analyze using statistics. For example, the user can select to analyze the tip amount attribute and examine univariate statistics such as the min, max, standard deviation, etc. for the taxi rides depicted on the map. Also, they can examine bivariate statistics like the Pearson correlation and covariance for the fare and tip amount. In the visual analysis panel below, they can select the types, metrics, and axes of the chart generated. Here, this bar chart depicts the average tip amount in relation to the number of passengers. Users can change the aggregate function and then the measure to analyze the maximum fare amount in relation to the number of passengers. Other chart types currently supported, besides bar charts, are line charts, area charts, and finally heat maps. to focus on and analyze a specific area, users can also draw a rectangle area over the map. For example, if a user wishes to specifically analyze the taxi rides that started from the JFK airport in New York City, they can draw a rectangle enclosing it like this. Thank you for your participation in this session, and I will be very happy to answer any questions. Please follow our developments in GitHub and find more information in our project web space. We will be happy to receive your feedback.